Traditional artificial intelligence operates as a simple probabilistic pipeline. Training exclusively on existing text, code, and images, it is entirely dependent on anthropocentric data. The system can only reflect our recorded knowledge back to us. It functions as a calculator trained on words, predicting the next logical token based on historical patterns. Synthetic intelligence marks a shift away from this reliance on human-generated datasets. Instead of parsing human text, an SI architecture utilizes advanced simulation environments and self-referential reasoning loops to generate its own training data from scratch. Traditional AI is reflective, looking backward at historical data to predict the next statistical step. In contrast, synthetic intelligence operates as a prospective system. This transition changes the fundamental objective of the system from task augmentation to genuine cognitive autonomy. It creates an engine capable of moving beyond human cognitive and experiential constraints. A linear language model generates outputs one token at a time. If it makes a probabilistic error early in its generation, that mistake compounds as the output continues, leading to structural failure. Pure neural networks are designed for open-ended pattern recognition, not strict deductive logic. Without rigid physical laws to govern them, they naturally hallucinate. To solve this, an SI architecture physically decouples the primary cognitive core into a network of separate active computational nodes. The open-ended intuition and semantic context of the neural layer are separated from a deterministic symbolic layer, which strictly enforces absolute logic. Queries no longer move in a straight line. They route through a multi-layered reasoning graph, where data loops recursively until it is validated. True autonomy is achieved by placing the generative engine inside a closed internal sandbox and mathematically proving outputs with a strict logic verifier before a final answer is ever produced. This technical blueprint illustrates the multi-layered architecture of a fully active synthetic intelligence system. The process begins at the orchestration gateway. This node evaluates the incoming prompt to determine if the user needs standard historical retrieval or recursive synthetic logic derivation. If synthetic derivation is required, the query routes into the cognitive sandbox, a secure internal computational workspace decoupled from the primary generative token engine. Here, the system writes custom physics simulations, compiles transient Python scripts, and builds temporary programs to practically test its theoretical concepts. The SI generates internal candidate answers and deliberately attempts to break its own logic to find the failure points in its reasoning. When an internal script fails, an automated evaluator feeds that negative result directly back into the engine, allowing the SI to iterate on its approach or branch to a new strategy. This allows the architecture to fail, learn, and iterate millions of times autonomously. It executes a complete internal scientific method before any output is ever generated. In this workflow, human engineers establish the mathematical boundary conditions. They set hard numerical limits on variables like manufacturing cost, weight, and thermal coefficients. The sandbox generates thousands of potential structures and passes the surviving hypotheses to the verifier. The verifier functions as a mathematical logic engine grounded in first principles, such as mass conservation and the laws of thermodynamics. It utilizes non-neural satisfiability modulo theories, or SMT solvers, to strictly enforce these rules. These solvers mathematically strip out neural hallucinations. The final output is restricted to concepts that are structurally grounded in physical reality. We can apply this architecture to a clinical challenge, diagnosing left ventricular wall motion abnormalities. Traditional clinical AI analyzes an echocardiogram video stream using computer vision to find pixels that correlate with past disease classifications. It does not understand physical cardiovascular anatomy. An SI architecture frames the diagnostic challenge as a physics-constrained electromechanical synchronization problem. The patient's one-dimensional EKG trace functions as the electrical command instruction, while the multidimensional echocardiogram acts as the physical kinematic execution. This PyTorch script demonstrates Phase 1, spatial temporal synchronization. The system parses the raw digital EKG trace to isolate microsecond markers of the R-wave peak, creating a spatial clock to perfectly sync the incoming video frames. The architecture then ingests a third data stream, acoustic cardiography, pioneered by Audicor Cardiometrics, which provides microsecond-level timing of heart valve events. These acoustic biomarkers provide a definitive mechanical anchor, linking the electrical command of the EKG to the visual movement seen on the echocardiogram. In Phase 3, first principles verification, the system evaluates a visual wall motion lag against hard causal constraints. If image noise from patient obesity or equipment artifact mimics a wall lag, the system's internal sandbox hydrodynamic simulation catches the mathematical contradiction and eliminates the false positive. By integrating acoustic physics into neurosymbolic logic, the system reaches a diagnostic conclusion based on causal reality rather than simple pixel correlation. This deterministic multimodal verification model scales beyond medicine into every facet of deep science and industrial R&D. Product development transforms from a linear human prototyping process into an evolutionary model. The SI architecture maps out complete multidimensional design landscapes, synthesizing thousands of geometric variations under simulated physical pressure. Because the system is not restricted by human aesthetic biases, it frequently renders highly optimized bioorganic blueprints that perform at efficiencies previously considered mathematically unreachable. The architecture acts as a cognitive telescope, bringing into view scientific realities that were previously conceptually or computationally unreachable. This transition introduces a systemic risk for expert practitioners, the black box epistemic crisis. Because SI explores vast multidimensional search spaces, it regularly arrives at correct, verified conclusions through pathways that human minds cannot easily track or retrace. As the SI autonomously handles the trial and error phases of research, including coding and data normalization, experts face a risk of skill atrophy and the degradation of their own foundational intuition. For the general public, living in an environment increasingly designed by these synthetic minds risks creating a deep sense of cognitive alienation. We are embedding deterministic symbolic frameworks within fluid neural systems, creating modular architectures that construct, verify, and enact independent logic.